Welcome to this video covering the geography syllabus. This video has been compiled by staff members of the geography department at St. L's School. We begin with a revision of the internal landforming processes. Earth movements are defined as lateral and vertical movements. They exert great forces of tension and compression, slowly producing features like the Rift Valley and escarpment. Horizontal movements cause several effects, which we will examine next. First, we have stretching. This is caused by tension or strain within the rocks, as the rock masses are pulled apart. This diagram illustrates the effect of stretching, which is caused by horizontal earth movements causing tension. The tensional process leads to tensional features, where the rock layers are stretched and thinned. Next is shortening. This occurs when compressional forces push rock masses toward each other, resulting in the shortening of the Earth's rocks. These diagrams illustrate earth movements causing shortening, driven by compressional forces within the crustal rocks. The compressional process results in compressive features, such as the folding of rock layers. Another process is shear or tear. Here, shearing horizontal forces move in the same direction, with the top layers moving forward more than the lower layers. This diagram visually represents shear or tear, where horizontal forces act in the same direction but with different magnitudes across the layers. Shear or tear can also occur when forces operate in opposite directions, displacing the rocks horizontally as they slip past each other. This illustrates lateral displacement, where opposing forces cause the rock masses to slip past one another horizontally. This final diagram shows shearing forces acting on the crustal rocks, demonstrating the movement along the layers. The resulting shearing features include lateral faulting, where rocks are displaced horizontally along a fault plane. Next, let's examine vertical movement, defined as movements operating along the radius of the Earth, from the interior toward the surface and vice versa. Vertical movement includes downwarping and upwarping. In folding, crustal rocks are pulled downwards or pushed upwards, which can be caused partly by compressional forces. These diagrams illustrate upwarping and downwarping of crustal rock layers. Vertical displacement due to faulting occurs when the middle block between faults may either subside or uplift. This is caused by compressional or tensional forces. Here we see the vertical movement caused by faulting, resulting in uplifted or subsided blocks of crust. Vertical displacement can also be accompanied by tilting. This is when the sunken or uplifted land is tilted, often due to compressional forces of unequal magnitude. This diagram shows vertical displacement accompanied by tilting, where the crustal block is inclined due to uneven forces. We now move on to examine the causes of Earth movements. One major cause is magma movement. Magma from the upper mantle can invade the Earth's crust, causing vertical or horizontal displacement of crustal rocks. Lines of weakness within the crust can be exploited by magma movement, leading to displacement. This illustrates magma movement causing crustal displacement as it forces its way through the crust. Another aspect of magma movement is the escape of large quantities of magma to the surface during volcanicity, leaving behind large cavities or voids in the upper mantle. This leads to gravitative pressure, as illustrated in this cross-section of the Earth's crust and mantle. Due to gravitative pressure, crustal rocks above these cavities move inwards to fill the voids, leading to subsidence or other Earth movements. Gravitative pressure is a key internal landforming process we are revising. This illustrates the forces at play within the Earth. Next, let's examine convectional currents. These currents circulate molten rocks cyclically within the mantle. They move inwards, towards the upper surface, then horizontally, and finally vertically inwards again. This diagram illustrates the convectional currents within the mantle, which drive significant Earth movements. Another illustration of convectional currents shows how the movement of molten material in the mantle influences the Earth's crust. We now look at isostatic adjustment. This refers to the state of equilibrium, known as isostasy, between the weight of the soil layer and the seama layer. The following two theories have been proposed to explain the internal landforming processes. The first is the continental drift theory. Proposed by Alfred Wegener in 1912, it suggests all continents were once a single landmass called Pangaea, surrounded by Panthalassa. This map illustrates the concept of continental drift over time, showing the breakup of Pangaea. This visual shows the supercontinent Pangaea before it broke apart into Laurasia and Gondwanaland. Evidence supporting the continental drift theory includes the jigsaw puzzle fit of continents, paleoclimatology data, and the distribution of coalfields beyond the tropics. Seafloor spreading and ridge formation further support the theory, showing new crust forming where plates diverge. Additional evidence includes similar geological structures across continents, paleomagnetic studies, and the resemblance of the Cape Folds of South Africa to those of Buenos Aires. The second theory is plate tectonics. It suggests the Earth's surface is composed of large tectonic plates that are constantly moving due to convectional currents. This diagram illustrates how plates slide in response to the forces generated by convectional currents in the mantle. Finally, we see a map showing the major tectonic plates of the world, highlighting the boundaries where interaction and movement occur.